Hello friends, in the previous lecture we considered that even though we are combining two different components, it is not necessary that these two components they form a solution. So when we combine two different substances, two different elements, it is possible for these two elements or these two substances to form what we refer to as the mechanical mixtures. So just because we are placing or just because we are attempting to dissolve two different components, it doesn't mean at the end of it we arrive at a solution. So that is understanding that we gained in the previous class. Now when you consider the behavior of the mechanical mixture to that of an actual solution, there is a difference that helps us understand what is the nature of the combination we have in our midst. Meaning when we have or when we attempt to combine say a component A and a component B, it is possible these two can form a mechanical mixture, or it is also possible that these two can form a solution. The way we can differentiate it is based on their behavior, particularly in the instance that we have considered. In the previous lecture we thought of a system in the vacuum and we poured the combination of these two components into that vacuum system. So we poured A and B into that vacuum system. Now this combination of A and B, the solution or this mixture of A and B, we did not ensure that it completely filled the vacuum, but we left some space for it such that the vacuum space is filled by the vapor of this combination of this mixture A and B. So in order to ensure that we have a vapor that combines both component A and B, we correspondingly built a system that consists of a vacuum and it is partially filled by the combination of components A and B. Now since a vacuum is not a low energy or a stable energy configuration, some portion of the mixture gets vaporized or gets evaporated. So since the mixture comprises of both A and B, the atoms, the components of both A and B, they evaporate and they fill the remnant vacuum section of the system. So what we essentially have is we have a vacuum system. In that we have filled it partially with A and B. Since the vacuum remains, we have the vapor phase that comprises of both A and B. So this vapor phase here, it comprises of both A and B. Now we saw that this vapor pressure that is introduced or this that is cumulatively introduced in the system, so this vapor pressure that is cumulatively introduced by both A components and B component, it varies depending on the nature of the mixture that is formed here. So that is what we looked into in our previous lecture. So depending on the nature of the solution we have, the nature of the mixture we have, the overall vapor pressure that includes the vapor pressure from A and the vapor pressure from B depends on the nature of the mixture. So what happens here in this vapor section depends on the nature of the mixture here. So what implicitly we have assumed is, in this study, what we have, or in this thought experiment, if you allow, what we have assumed is, once you introduce the liquid, be it A alone or B alone or combination of A and B, we are studying a case where the equilibrium is established. We are not considering a dynamic case, or we are not considering a transition towards the equilibrium. We have assumed the system has reached an equilibrium, a stability has been reached within the system, and that allows us to relate the rate of evaporation to that of the rate of condensation, meaning in this system what is established is not a static equilibrium but a dynamic equilibrium, meaning whatever transition, if because of the contact between the atoms in the vacuum and or in the vapor state to that of its corresponding mixture in the liquid state, because of this interaction, if some of them get absorbed in the liquid state, there is a corresponding reverse reaction of the liquid getting transformed into vapor phase. Some components of the liquid or equivalent components of the liquid getting transformed into the vapor phase, and this is what we refer to as the dynamic equilibrium. So we are considering a specific case, a specific system, a specific instance in the system. So we are considering a vacuum partially filled with a combination of A and B, and we are considering an equilibrium that has been established in A and B. And again, since the equilibrium needs to ensure that whatever rate of evaporation is there, it needs to be equivalent to the rate of condensation, and it is the condensation is possible only when you have the sufficient amount of interaction between the atoms in the vapor state with the atoms in the liquid state, and this is possible only when you have appropriate vapor pressure. We have this expression here. Now, in case of the mechanical mixtures, so mechanical mixtures are characterized by the behavior of the individual elements in the mixture, meaning these elements, they are not mingled, they are not mixed with each other, they continue to remain as they are, as though they are in their elemental form. Even though they are mixed in the mechanical mixture, they behave as if they are in their elemental form. So one way of identifying is that they bond with only their similar kind of atoms. So the bond that is found between the similar kind of atoms. So this is one of the characterizing features of the mechanical mixtures. Now in that case, this expression, the pressure that ensures that a dynamic stability is established between the liquid and the vapor phase, is equal to the concentration, the product of the concentration and the saturated vapor pressure of the individual components. And here we have represented it in the form of mole fraction, meaning it is the ratio of the number of moles of A or the number of atoms of A to that of the total number of moles of atoms that is present in the system. So this is what we refer to as the mole fraction. Now we saw in our previous lecture that while introducing or while representing the concentration and mole fraction, it allows us to reduce the number of independent variables, meaning since the summation of the mole fraction of the different components that are present in the system is equal to 1. Now you can derive this by substituting or by expressing in the similar way what is the mole fraction of B, and summing it up you will get this is equal to 1. Now since this summation holds for the mole fraction, the XB, the concentration of the other component or the other element, can be expressed in terms of the original one. So the concentration of solute can be expressed in terms of the solvent. So this is the reason why we have represented or why we have adopted to express the concentration in mole fraction. Now the overall vapor pressure when you have a mechanical mixture is the direct relation between the concentration, the summation of the product between the concentration and the saturated vapor pressure. Now when we graphically represent it, we saw that we need 2 points. Supposing along the x-axis we consider the concentration of B, so it starts from 0 to 1, and since we have this relation here, it can also be treated as the reversal of XA, 0 to 1. So the XB increases in this direction and the XA correspondingly decreases in this direction. Now when I have a system that is completely filled with A alone, element A alone, in that case the partial pressure of B is 0, so we have one starting point here, and when the system is completely filled with B, then we have an equilibrium established between the B and the B liquid and its vapor, and that is established through the saturated vapor pressure. So we have the saturated vapor pressure of B here. So this extreme, the left extreme indicates pure B, the right or rather the right extreme indicates pure B, the left indicates it represents the absence, the complete absence of B. So therefore we have two different points here, and there is a linear relation, so it can be expressed in this manner, can be graphically expressed in this manner. Even though it is a schematic representation, the essential aspect of this representation or essential aspect of the numerical relation is captured. In the same way, we will be able to do so for the A, and ultimately the overall pressure can be expressed by connecting these two, meaning we have 2 points, that is assuming XA equal to 1 and XB is equal to 0, we get this point here, and assuming the reverse of it, XB equal to 1 and XA equal to 0, we get the other point here, and since it's a linear relation, we will be able to relate this point to the other point, and we ultimately end up with representing graphically the vapor pressure for the mechanical mixture that ensures for these different concentration the system is set in the dynamic equilibrium. The system exhibits a dynamic stability. So if you consider this concentration, this combination of concentration here, this would be the vapor pressure for the mechanical mixture. In order to ensure there is a stability in the system, a dynamic equilibrium is maintained. The same goes for this concentration here. We need to remember each of these points represent individual concentration. For individual concentration, we need individual vapor pressure in order to ensure that there is a dynamic equilibrium that is established for mechanical mixture. This straight line here, so let me highlight it in red. So this straight line here indicates what that equilibrium pressure is, what that pressure is that establishes this dynamic equilibrium. Now, we also saw that as opposed to the mechanical mixture, we have an actual solution where, in addition to the bonding between the like atoms or like components, there is also a bond that is established between the unlike components, which in this case, since we are just considering two components or two elements, a binary system, there is a bond that is formed between the unlike components, that is A and B. Now, when we have a formation of an unlike bond such as this, now the amount of atoms that are present or the amount of component that are present in the vapor phase not only depend on these bonds but also depends on these mixed bonds. So these are like bonds and these are unlike. So if you treat this as like bond and if you refer to them as unlike bond, now the total number of atoms that are present in the vapor phase, it not only depends on the like bonds but also it depends on the unlike bond, meaning so these bonds are formed in the liquid phase, these bonds are found in the liquid phase, or these bonds are found in the solution. Now when these components needs to occupy the vapor phase, they need to break away from these bonds. So in this case, in the mechanical mixture, they need to break away only from the like bonds. However, in case of solution, they need to break away from the unlike bond in addition to the like bonds. So therefore, whatever vapor pressure is established in the system, it not only depends on the like bonds but also depends on the unlike bond. So depending on how the energy of the like bond is when compared to that of the energy of the like bonds, so how the energy of the unlike bond is in relation and compared to the energy of the like bonds, the concentration of the amount of the individual components in the vapor pressure varies. So depending on the inner bond energy of the like and the unlike bonds, the amount of components that are present in the vapor phase varies. So therefore, when you have a solution, a linear relation can no longer be expected. So that is what a gist of what we have considered in our previous lecture. So it is possible for us if we combine two different elements. Now, instead of using more general terms, let us now restrict ourselves. Let us again narrow it down to our area of interest, which is restricting it to the material system, particularly the metallurgical system. So therefore, we refer to this A and B as individual elements. So we saw in our previous lecture, the key takeaway from our previous lecture is that even though we attempt to combine two different elements, it is not necessary that they form a solution directly or they form a solution spontaneously. It might be possible that they initially form a mechanical mixture or they form a mechanical mixture, or it is also possible they form a solid solution. So therefore, there is, just because we combine two elements, it does not mean that we should expect a solution at the end of it. Before applying this understanding to the areas where we are interested in, the areas or area of our interest, let us consider one parameter that helps us understand the behavior of the individual component, the behavior of the individual element. It is referred to as the activity. So activity in this case, it refers to, as the name indicates, it refers to how active a given component is, how active a given element is in the system. So the activity of a given component in the system, the activity of a given element in such a setup, it depends on what is its vapor pressure. So the greater an element is active, the greater it will be able to break away from the liquid state and to occupy, or it will occupy the vapor phase. So the activity, as the name indicates, is how active your element is within the given framework, and it is rather quantified by its corresponding vapor pressure. So when we are considering the activity, no two elements in a given mixture, they exhibit a same activity. So therefore the activity is different from, or it is restricted to a given material. So activity is a material parameter. Of course it depends on the environment, the amount of the nature of the solution it is presented. However, it is a material parameter. So activity of A is often different from the activity of B. Now the activity of A, again like I considered, is often represented by A, and we are considering the activity of element A is equal to the ratio of the partial pressure of A to that of the partial pressure or saturated partial pressure of A. So this partial pressure of A is in the presence of a solution. So, and the saturated vapor pressure is when you have only the elemental form of A. So when you consider two instances, or when you consider the activity of A in a solution, it is nothing but the ratio of the vapor pressure of A because of that solution and the vapor pressure of A when it is present alone in its elemental form. Now for a regular solution, or rather pardon me, for a mechanical mixture, we have already realized, or we have already related the partial pressure of A in a given solution to the partial pressure or to its corresponding saturated partial pressure, and it is related through its concentration. So this we saw in our previous lecture, and this is what we refer to as the Raoult's law. And for a mechanical mixture, for a Raoultian solution, what we end up having is we will be able to substitute or replace the partial pressure of A in the solution, and therefore we can express the activity as in this manner. These two gets cancelled out. So activity of a component in a mechanical mixture or a Raoultian solution is nothing but its corresponding concentration expressed in mole fraction. However, when we consider a solution, there is, even though there is a relation that exists, or there is a direct relation that exists between the activity of A and the corresponding concentration, it is not as equivalent as we observe in the mechanical mixture. So the difference is, when we consider the activity of a given component in a mechanical mixture, it is equivalent to that of its concentration. However, in an actual solution, even though there exists a direct proportionality between the activity of component and its concentration, because the same can be conceptually understood by how the presence of the vapor state, the amount of A present in the, so amount of a component present in the vapor phase depends on the bonds that are present, and how easy it is for us to break away from these bonds, or how difficult for us to break away from these bonds. These bonds can only be formed when you have sufficient amount of A and B. So therefore the activity, which is nothing but the ratio of the pressure of a given component to that of its saturated vapor pressure, even though it is proportional to that of concentration, because only when you have sufficient concentration, this concentration is reflected in the pressure. When you have high concentration in the liquid, you will have correspondingly or relatively high concentration in the vapor phase, provided the bond energy between the components are relatively similar. So when you assume the bond energy between the concentration are relatively similar, then what essentially we have is, when you have high concentration in the liquid, you have proportionally high concentration in the vapor phase. So therefore, even in the solution, there is a direct relation between the activity and the concentration. However, it is not as equivalent as we observed in the mechanical mixture or in the Raoultian solution. So therefore, there is a constant proportionality that is involved, and it is generally expressed in this manner. So activity is some term that you might come across in the future, or it will be involved while describing the nature of a component in a solution as well. So therefore, I just wanted to introduce this particular parameter, this particular terminology here. Now, let us attempt to rather adapt or extend this understanding to the solutions we are interested in. So far in this discussion, we have considered a specific system. So this system involved a vacuum, and this vacuum is partially filled with a fluid. So that is what our starting point was. Now, even though that is where we started, but our intention is to understand the behavior of the solid solution. Our interest in the goal is rather to extend the understanding that we gained from that specific setup to understand the solid solutions or alloys. Now, in case of solid solutions or alloys, one key parameter that is different is that, or the key parameter that distinguishes solid solution from the alloys from their elemental state is that they comprise of more than one components. They comprise of more than one elements or components, and one that occupies the, or that is of greater weight percent, we refer to that as solvent. And because we are treating it as a solid solution, we have solvent and solutes, and these solutes are often referred to as the alloying elements. So these terminologies we have hinted at in the previous lectures. Now, when you consider a solid solution, and when you want to describe the energy of the solution, or let's say a change in the energy of the solution when it is experiencing a change, then we often adopt the Gibbs law or the Gibbs free energy, because in addition to being influenced by the temperature and pressure, the variables that is more accessible to us that can be changed in the laboratory condition, these are also then dependent on the number of moles of the individual components, the individual elements that are present in the system. So, when we assume a solution that comprises of k elements, so 1, 2, 3, so on and so forth to k, then the change in the Gibbs free energy is dependent on temperature, pressure, and the number of moles of 1, 2, 3 and k elements. Now, this change in the Gibbs free energy, because all these are the state variables, can be expressed as, the overall change in the Gibbs free energy can be expressed as. So now before doing that, let us make a simplification. Let us treat this individual components, the amount of individual components, as a capital N. So the capital N includes the amount of individual components from 1 to k. So now the change in the Gibbs free energy is equal to the change in the Gibbs free energy with respect to temperature when pressure and all the other components are constant. And similarly, we change the Gibbs free energy with respect to pressure when the temperature and all the other components are constant. And finally, we have the change in the Gibbs free energy with respect to, the change in the Gibbs free energy with respect to the change in the components when temperature and pressure are constant. So now what we essentially have is, we are now able to express the change in the Gibbs free energy when there is a change in the state of the system that includes n number of components, n, or rather k number of elements in it. Now assuming that the temperature and pressure are constant, so that means these two terms get cancelled out. The overall change in the Gibbs free energy is now dependent on the change in the Gibbs free energy with respect to the individual components alone. So now we have already seen that the change in the Gibbs free energy with respect to its individual components, we refer to it as the chemical potential mu I. Correspondingly, the change in the Gibbs free energy is expressed as in this manner. Now what we essentially have is, we have a Gibbs free energy, change in the Gibbs free energy that is related to the chemical potential and the corresponding change in the components, the corresponding change in the amount of element that is present in the system. So when the amount of element changes, the Gibbs free energy correspondingly changes based on its chemical potential. So that is what this expression indicates. Now this is nothing but an extensive variable that is dependent on the amount of component present, meaning this depends on this variable here, the Gibbs free energy. This is something that we considered earlier. This is a variable that depends on the amount of components that are present. So then we have to, when we consider the relation between G and mu, so Gi and mu, let's say, what we have is, here this is an extensive variable. This is an extensive thermodynamic function that depends on the number of the specific elements that are present. Here it is an intensive thermodynamic variable that is independent of the number of variables that are present. So given this description, it is possible for us to write this expression as, so instead of considering the change, the actual Gibbs free energy, because this is an extensive and this is the intensive variable of describing the same system, describing the same aspect, describing how the system behaves with the change in the number of components present, with the change in the number of atoms present in the system. Both these describe when the system is at constant pressure and temperature. Both these describe the state of the system for a given composition, for a given number of atoms. The relation between these two, this is an extensive variable and this is an intensive variable. They both describe the state of the system that comprises of too many or several components, and the difference is that this varies with the number of components. This does not vary with the number of components. This is extensive and this is intensive. So therefore these two can be related from this expression as summation of, again, change in the Gibbs free energy. We are considering just the Gibbs free energy here as the summation of ui and ni. So this expression here describes the change in the Gibbs free energy, whereas this, from this expression now we are describing the Gibbs free energy, not the change in the Gibbs free energy. This we are able to arrive at because these two are more or less, these two describe the similar aspect of the system, the similar feature of the system. It describes the state of the system based on its concentration, whereas one is extensive, the other is intensive. So therefore the relation that we have is this. So we are able to express or arrive at this relation that is mentioned here. So the Gibbs free energy is equal to the summation of the product of the chemical potential and the number of components that are present, or the number of moles of the components that are present in the system. So I hope you are able to relate or able to understand how we arrive at this relation. One is extensive, the other is intensive. So this extensive is, the only difference is that the extensive depends on the number of moles of components that are present. So now we have related the intensive to that of the number of moles of components, thereby giving us the extensive function of this variable here. So this variable multiplied with the number of components, this is intensive variable multiplied with the number of components, gives us the extensive function, which is dependent on the number of components that is present in the system. Now let us go back to our consideration of the binary system, which comprises of components or elements A and B. So in that case, the Gibbs free energy of this binary system A and B can be expressed as the chemical potential of A and the number of moles of A that is present, and the chemical potential of B and the number of moles of B that is present. Now it is possible for us to divide both sides by the summation of the total number of moles of components that are present in the system. So this is the total number of moles of components that is present in the system. So we can divide both left and right side with this term here. So ultimately what we end up having is, we end up having something like this: mu A x A. So we will be replacing the number of moles with mole fraction, mu B x B. So we end up having this expression. So the reason we multiply this both on the right hand side and the left hand side is to replace the concentration or express the concentration in the mole fraction. Now this term here, it indicates the Gibbs free energy of the solution per unit mole. So the solution comprises of, this mixture comprises of A and B, and this term here, it indicates the Gibbs free energy per unit mole. So per mole of the solution, what is the Gibbs free energy is what this ratio here indicates. So therefore we can replace it by Gm, or let's see, G bar. Now the G bar is equal to mu A x A plus mu B x B. Now this expression is something similar to what we saw in our previous case. Now in our previous case, for our specific consideration of a solution in the vacuum, we had for mechanical mixture, the pressure that is established in the vapor state is equal to the product of the concentration of the pressure, or the product of the concentration of a given component to that of its saturated vapor pressure, and the sum of the next one as well. So this is an expression we arrived for a consideration involving vacuum and a solution, and this we were able to represent in a graphical manner, meaning we were able to consider two different extremes and the relation between these variables to that of the overall function, and we were able to express it in a graphical manner. So let us try to do the same. Now let us consider how G bar varies with the concentration of A and B. So let us assume along the x-axis it is xb. So it on the left extreme it is 0, on the right extreme it is 1. So since these are expressed in mole fraction, it is possible for us to have to represent xa, that is the other component as well. So here it is the reverse of xb. So along the left extreme you have xa equal to 1, and along the right extreme it is 0. Now let us consider these two extremes, meaning let us assume or let us estimate what will be the Gibbs free energy per mole of the solution G bar will be when the solution that we have is exclusively comprises of xa. So when the solution we have exclusively comprises of the element A alone, then xa will be equal to 1 and xb will be equal to 0. So that means this term vanishes off and this term here will be equal to 1. So in that case the Gibbs free energy per mole of the solution will be equal to mu A naught. So let us assume or introduce a naught in order to indicate that this is the Gibbs free energy per mole when you have a solution that comprises exclusively of A. So when you have a solution that comprises exclusively of A, it indicates the left extreme here. So here in the y-axis we are plotting G bar. So it indicates the left extreme here in the graphical representation. So when you have a solution that is exclusively of, that comprises exclusively of element A, you have a specific value that is indicated by mu A naught. Now same way we can have a solution that comprises exclusively of B alone. In that case the xb will be equal to 1 and xa will be equal to 0, and the corresponding Gibbs free energy per mole of the solution will be equal to B naught, and this will be something, let us assume that this will occupy a position on the right extreme and it is something like this. Now this expression here that indicates what will be the Gibbs free energy per mole for the mixture of A and B. It exhibits a linear relation between these two points, these two endpoints. This expression indicates a linear relation. So therefore what we end up having is a representation of this form. So this means the Gibbs free energy of the so-called solution that we have, the so-called combination that we have, it follows a linear path. And this linear path, it connects two extremes. One extreme wherein you have the Gibbs free energy per mole of the component A alone and the Gibbs free energy of per mole of component B alone at the two extremes. So this is the nature of how the Gibbs free energy changes when you have the mixture of A and B. Now from our understanding of how a mechanical mixture behaves, it is possible for us to state that this indicates, this is similar to that of the relation that we observed in mechanical mixture. So therefore this cannot be a solution. So it is possible for us to state that this cannot be an actual solution because this is a behavior that we observed in the mechanical mixture. So in order to understand that, in order to say, or in order to ensure that this is not a solution, there is a solution that is possible, let us differentiate the values that this line gives to that of what could be the Gibbs free energy when an actual solution is formed. So let me repeat, what representation we have is something like this. The representation now with us is of this form here. So we have xb that is varying from 0 to 1, and the way the Gibbs free energy of the solution per mole changes is between, it changes between two values, it varies between two values and in a linear fashion, and our understanding helps us, our understanding states that this is possible or this is similar to what we observe in the mechanical mixture. So from our understanding of the mechanical mixture, we can rather postulate or at least conceive that it is possible that there is a solution that deviates from this linear relation. We saw that in case of our previous discussion, when a solution occurs or when there is a possibility of solution that is formed between the two components, one indication of the solution is that it deviates from this linear relation. So therefore, when you have a solution that should deviate from this linear relation here. So therefore, whatever Gibbs free energy function that we have, let us consider it or let us assume that it is for the mechanical mixture. So this function that we have so far, which is directly or which is in linear relation with the concentration, so this is something that we have derived now. So this, let us assume that it is because of its similarity to the mechanical mixture. Let us assume that this is for the mechanical mixture. Now, we saw from our understanding of the thermodynamics of solution, we can state that there should be a different function for the Gibbs free energy for the solution, because that's what we saw when we compared the mechanical solution to that of the actual solution. When we compared the Henry's laws to that of the Raoult's law, there was a deviation from the linearity. So if you could recollect, we saw in our previous lecture that when you compare the Raoult's law to that of the Henry's law, there is a deviation, and this deviation is from the linearity that you observe. So this is something that we considered in the previous lecture. So meaning when a solution is established, this linearity is disturbed. So we saw either the relation or the change in the Gibbs free energy in this case, or the change in the partial pressure in our previous discussion. It adapts a form like this or it adapts a form like this, depending on the way the energy, the bond energy between the dissimilar atoms varies. You either adopt a overshooting curve or an undershooting curve. Now, since the Gibbs free energy of the solution is a function that is different from the Gibbs free energy of the mechanical mixture, it is possible for us to rather estimate or quantify what would be the difference in this Gibbs free energy. So the Gibbs free energy of the mechanical mixture is different from that of the Gibbs free energy of the solution, because there is a difference. Again, relating it to our understanding of thermodynamics of solution, since there is a difference, so we can use the delta G to quantify the difference between the Gibbs free energy of the mechanical mixture to that of the Gibbs free energy of the solution. Now, this difference is rather indicated by the deviation from the straight line. So that is what we saw in our previous lecture, or that is how we perceive the Henry's and the Raoult's law. So the Henry's law, it considers the actual solution. The Henry's law is no longer linear. However, the Raoult's law is linear, and this deviation from the linearity is because of the difference in the pressure that is introduced in the solution. And this difference in the pressure is what brings about the non-linearity. Now, this difference in the Gibbs free energy, it is possible for us to rather, even though it is also possible for us to estimate exactly what this value could be, it is possible for us to quantify it. Let us treat what this difference in the Gibbs free energy would be in a qualitative manner. So the difference in the Gibbs free energy in its canonical form can be expressed as in this manner. So we have an expression for the difference or the change in the Gibbs free energy. Supposing a mechanical solution or a mechanical mixture changes to solution, then there is a change in the Gibbs free energy, and it means this term here should be less than 0. Meaning you have a mechanical mixture transforming into a solution. So the mechanical mixture has its characteristic Gibbs free energy. The solution has its own characteristic Gibbs free energy. So there are two states possible. Mechanical mixture is one state, the solution is the another state. Now, a spontaneous change from the mechanical mixture to solution. A spontaneous change is possible only when the change in the free energy is less than 0. Only when the Gibbs free energy of the solution is less than that of the mechanical mixture. So only when this criteria is satisfied, you will be having a solution instead of a mechanical mixture. So I hope you are able to understand that. So this difference in the Gibbs free energy that enables us to have a transition from the mechanical mixture to solution can be expressed in this manner. So we can use this expression to rather estimate the difference in the Gibbs free energy that allows for the spontaneous change from the mechanical mixture to solution. Now, when we consider this expression, it is possible for us to have a solution wherein the change in the enthalpy, the corresponding change in the enthalpy is equal to 0 or it is close to 0. So, in the first instance, this is assume a first instance wherein we have a mixture, we have a solution that is forming, and we have a solution, and in that solution, during the formation of the solution, the enthalpy change that occurs is negligible. So therefore, the change in the Gibbs free energy is completely dependent on, in this case, is completely dependent on the change in the entropy alone. So what we are considering is, we have initially identified that when we combine two components, when we combine two elements, it is possible either for it to form a mechanical mixture or a solution. Depending on which form it adopts, which configuration it adopts, it has its corresponding free energies. Now, the corresponding free energy for the mechanical mixture is linear and for the solution is non-linear. Now, we are considering a state wherein the solution is more stable than the mechanical mixture. So therefore, even though initially you form a mechanical mixture, since the solution is of a low free energy, the mechanical mixture is getting transformed to the solution. Now, the driving force, the difference in the free energy that enables this transition from mechanical mixture to solution is quantified in this expression here. Now, in order to describe it qualitatively, not quantitatively but qualitatively, in order to discuss or to understand this driving force, we are considering a solution where the change in the enthalpy when the mechanical mixture changes to that of solution is 0. So in that case, what we essentially have is, we have the change in the Gibbs free energy that is entirely dependent on the change in the entropy. Now, we have seen that the second law of thermodynamics helps us understand that whenever there is a change in the entropy, the only change that is possible is the increase in the entropy. The entropy can remain unchanged or it can either increase. So the decrease in entropy is not observed in the physical world. The only place where the decrease in entropy is observed is in machine learning. So that is a totally different world. So therefore, in the real world, the only entropy increase is possible. So in that case, when you have such an expression here, when you have such a solution here where there is no change in the enthalpy, then the mechanical mixture changes to a solution, then what we ideally have is a negative change in the Gibbs free energy. So ultimately, the solution is a more stable state than the mechanical mixture. So therefore, when you have a system that combines two components and when it combines, there is not much enthalpy change, then it depends on the entropy alone. So therefore, instead of forming a mechanical mixture, the system forms a solution. Now, let us try to illustrate how this change in the entropy would be. So this change in the entropy can be represented in different ways. So one description for the change in the entropy, or we have introduced the concept of entropy in different ways. One is the degree of irreversibility, whereas the other is the degree of randomness. While introducing the concept of entropy, we introduced this understanding that entropy can be viewed as in different ways. One way of viewing it is the degree of irreversibility, and the other way of viewing it is the degree of randomness. So when we consider this understanding of the entropy, or this view of the entropy as the degree of randomness, we can graphically represent the change in the entropy, how the entropy changes with respect to the concentration. So we have this expression here, or this illustration here, which represents how the Gibbs free energy changes for the mechanical mixture with respect to concentration. And we are trying to arrive at, or we are trying to understand how the solution, the Gibbs free energy of the solution changes with respect to concentration. So one parameter that is involved is the entropy. So therefore, we need to consider the identical variable, that is the concentration xb. So again, the xb, it starts from 0 to 1 along this direction, and XA correspondingly it starts from 0 to 1 in the opposite direction. Now a qualitative understanding of this entropy would be something like the entropy when in these two extremes, when you have the same component, similar components alone, when you have exclusively the elemental form of A and the elemental form of B, it is where the entropy will be at its lowest, because the entropy, again the degree of randomness, you need different components to be arranged in a different way in order to achieve an extensive randomness. When you have only one form of quantums that is present, then in that case the entropy will be at its lowest. Now as the impurity, as the other components or other atoms begins to increase, the amount of the randomness that can be introduced also increases. So therefore when we move along this direction, what we are doing is, when we move along this direction, what we are doing is, to pure A we are introducing B. So therefore the randomness increases and it keeps on increasing till a particular point, and after a particular point it begins to decrease. The reason it increases till a particular point is that the degree of randomness, it does not depend on which component largely we are playing with. So it all considers is the difference between the two atoms. So initially from this to this, from this point to this point, so this point it indicates 0.5%. So this point here it indicates 0.5% of the B. From this point to this point here, you have the ratio, when you consider the ratio of, or when you consider the relative difference between the one component and the other, it keeps on increasing. So since the summation is 1, so this is the maximum. So the relative difference, or in the concentration of one component or one element with respect to the other, it keeps on increasing from 0 to 0.5. And when you move away from 0.5, what you essentially have is, you establish the B as the solvent and A as the solute. From 0 to 0.5, you have A as the solvent and B as the solute, and from B, or from 0.5 to 1. So you have two sections here, from 0 to 0.5. Since A is of maximum concentration, so A will be a solvent and B will be the solute. From 0.5 to 1, B will be the solvent and A will be the solute. Despite this difference, when you consider, despite this change, when you consider the difference in the concentration, both this and this remain the same, both this and this, they remain symmetric, and therefore you have such a curve that represents the degree of randomness, the change in the entropy in the solution. So this is the nature how the entropy changes for the solution. And now what we have is, we have a negative sign before it. So therefore when you include the negative sign along with the temperature, you end up having a curve of this form that represents the change in the entropy when you have the combination, when you have the dissolution of A and B. So this curve, now we will be able to combine it here in order to capture the Gibbs free energy of the solution. So this is where we will begin in the next lecture. We will try to represent now the Gibbs free energy of the solution by using or by introducing the change in the entropy. Goodbye.